We're now going to consider exponential and logarithmic functions to bases other than e. So in this video, we're going to look at the relationship between the natural exponential function e to the x and other exponential functions a to the x, where a is a number other than e, as well as the natural logarithmic function and logarithmic functions to base a. Now, to start, let's recall this. Recall that e to the natural log of u equals u. That's a property that the natural exponential and logarithmic functions have, since they're inverse functions of each other. And so we see that if we think of a to the x as being some number, it has the property that a to the x equals e to the natural log of a to the x, that same number. And so what we can do is we can take this x here in the exponent and drop it down in front of the natural logarithm. And we obtain this definition for a to the x. So then a to the x equals e to the x times the natural log of a. So this gives us a way of defining a to the x in terms of the natural exponential function e to the x, which we've already defined. So here we have a definition then. So if a is a positive real number not equal to 1, and x is any real number, then we can define a to the x to be e to the x times the natural log of a. So this gives us a definition for a to the x and a relationship between that function and the natural exponential function. Now, the reason we don't want to let a equal 1 is because in that case we just get a trivial function. Notice that if a is 1, 1 to the x equals e to the x times ln 1, and this term is 0, the natural log of 1 is 0, so we get back e to the 0, which is 1. So that's just a constant function. Now let's take a look at this example. So if we want to express 2 to the x in terms of e, well, all we have to do is follow this definition right here. So 2 to the x is going to be e to the natural log of 2 to the x, and just drop that x down in front of the ln, and we obtain this. So this is what 2 to the x power is in terms of the natural exponential function e. Now let's consider this example. So suppose we have 100 grams of some radioactive substance with a half-life of 15 years. So that means that in 15 years, half of the material will have radiated away. And that process continues every 15 years. Let's find a model that can be used to determine the amount of material left after t years. So we're going to try to create a model in terms of an exponential function. So let's create a little table over here to try to model this problem. So t is going to be years, and the half-life is 15, so let's go in increments of 15 here. So 0, 15, all right. Now, at time 0, you initially have 100 grams of the substance. Now, after 15 years, that's going to be cut in half. So the amount of material that you have is going to be 1/2 of 100. So 1/2 times 100. And let's leave it like this instead of writing it as 50, because we'll see a nice equation come out if we leave it like this. In another 15 years, you'll have 1/2 of this amount left. So in other words, you'll have so that's how much you'll have left. Then in another 15 years, or after 45 years, you'll have half of this amount remaining, so you'll have, and then in another 15 years, or after 60 years, you'll have this amount left. So now we want to come up with some type of equation for the amount of material Q as a function of time t in years using the information that we have up here. Well, notice the amount of material that we have after time t is going to be 100 times, well, notice we have 1/2 here. This is 1/2 to the 1 power, 1/2 to the 2, 3, 4. But over here in this column, we go by increments of 15. So what it's going to be is this, 1/2. So we want to put up here in the exponent some function of t that takes 15 to 1, 30 goes to 2, 45 goes to 3, and 60 should be 4. Well, if you think about that for a little bit, what we'll put up here in this exponent is going to be t divided by 15. You see, that way when t is 15, I get a 1 up here, which is what I want. When t is 30, we get a 2 right here, which is what we want. When t is 45, 45 divided by 15 is 3, and so on. So this is our equation then that models the amount of material after t years. And notice it is an exponential function where the a is 1/2 in this case. Now we could rewrite this as follows. Using our definition for a to the x, recall that we can then write this as so we can write it like that, which notice also the natural log of 1/2. 1/2 here is 2 to the negative 1. So if we bring that negative 1 out in front of the ln, we could write it as negative the ln of 2. That's a little nicer than having the ln of 1/2 there in our exponent. And so this then becomes and so here's a nice model for the amount of material left after t years. So for example, if we wanted to know how much material was left after 70 years, we could just evaluate and just be careful when you evaluate this on your calculator. You would have to put the exponent here in parentheses. So you would have to enter this as and then evaluating on this calculator, we get approximately 3.937 grams. Now, of course, you could also evaluate this on your calculator. Calculators can handle this as well, so you could have also just entered so you could just type that into a calculator and you'll get the same answer. And before we look at our next example, let's note one other thing here. Sometimes you'll also see this function written like this, noting that 1/2 is 2 to the negative 1. You can also write this as right, since 1/2 and then you just multiply the exponents here. So sometimes you'll even see it written like this. So here's 3 different forms for this answer. This one, and then our exponential form down here. Now let's take a look at this. So now we want to take a look at logarithms to the base a and their relationship to the natural logarithm. So here we have a definition for a positive number a that's again not equal to 1, and given any value x, we define the log base a of x to equal the number y if and only if a to the y equals x. So in other words, the log base a of x is supposed to be a number y in which a to the y equals x. Or we could even write it like this down here. A to the log base a of x gives you back x. So for example, let's evaluate the following quantities to get a little better handle on this definition. So let's evaluate log base 10 of 100. What's that supposed to be? Well, that's supposed to be a number y in which 10 to the y should give us back 100, right? Using this definition right here. Well, obviously then, y should be 2. So therefore this quantity is equal to 2. It's as simple as that. What's log base 2 of 8? Well, that's supposed to be a number y in which 2 to the y gives us back 8. Well, obviously then y should be 3. So this quantity here is equal to 3. Let's try one more. How about log base 3 of 1 over 27? Well, that's supposed to be a number y in which 3 to the y equals 1 over 27. Now, what should this y equal? Well, let's note that 1 over 27, is 27 to the negative 1 power, and 27 is 3 cubed, right? So this is actually 3 to the negative 3rd power, right? You see, 3 to the negative 3rd is 1 over 3 cubed. Always keep that in mind. You have to recall your rules for exponents when we're doing this material. A to the negative x is 1 over a to the x. You must review all your rules for exponents. So 3 to the negative 3rd is 1 over 3 cubed, which is 1 over 27. So therefore, the y right here must equal this quantity right here, so negative 3 works. So therefore, this quantity is negative 3. Let's try one more like this before we leave. What about log base 2 of 1/16? Well, this is supposed to be a number y in which 2 to the y equals 1 over 16. Now I know that 1 over 16 is 2 to the negative 4th, right? Because you see 2 to the 4th is 16, right? 2 times 2 times 2 times 2 is 16. So 2 to the negative 4th is 1 over 16. 1 over 2 to the 4th. And so therefore the y should be negative 4. So log base 2 of 1 over 16 is negative 4. Now let's take a look at the relationship between these log base a's and the natural logarithm. Now let's recall this. The natural log of x equals y if and only if e to the y equals x. Right? Recall that. And this is because e to the ln of x equals x. So this is basically because of this property right here, because e and the natural logarithm are inverse functions of each other. So therefore, if we think back to the definition we had up there earlier, recall that this was our definition, log what we see here, this definition right here looks just like this one, with the a right here being the e. So what we see here is that actually the natural logarithm then is really a logarithmic function to the base e. So actually the ln of x is really log base e of x, because it follows exactly this rule right here when a is equal to e. Now let's take a look at the relationship between log base a for any a and the natural logarithm of x. So here we have a theorem, and it states that log base a of x equals ln x divided by ln of a. So let's take a look at the proof of that. So let's start out with this. Okay, so this exactly means that is the same as saying, it's the same as that, right? That's our very definition for log base a of x. Now what we're going to do is we're going to take the natural log of both sides. So there, we took the natural logarithm of both sides. Now notice we can drop this y out of the exponent here by properties of the natural logarithm, and we get that this is the same as, and now we're just going to divide this quantity here underneath the natural log of x, and we obtain that and now recall that y is equal to this quantity up here. So if I put this in place of the y, we get that this quantity is equal to, and there you go, we have our proof completed. That's exactly what we wanted to show right here. So let's take a look at a few examples now. So let's evaluate log base 3 of 25. Now, your calculator doesn't have a log base 3 button on it. It has a natural logarithm button. It probably has a log base 10 button if you look for it, or if you have a scientific calculator, it'll have that on it. But it doesn't have a log base 3. Well, that's okay, because as long as it has a natural logarithm button, we can still evaluate this. So this quantity here will equal and now we can evaluate each of these on our calculator and divide them, and we get approximately 2 point, and there we go. Let's take a look at one that we looked at earlier and verify that we'll get the same result if we do it this way. Recall that we had this quantity was -3, and that's because 3 to the -3 gives us back 1 over 27. So this quantity right here is log base 3 of 1 over 27. So if we use this formula right here, let's just verify that we do get back -3. So this quantity using this formula should equal, and sure enough, if you evaluate this on your calculator, you will get -3. And also note that we really don't even need to evaluate it on our calculator. It'll actually simplify to this. Notice that we could actually write this as and then just dropping this right out of the exponent here, we get that this is equal to, and these cancel, and of course we get back -3. But of course, if you just evaluated that on your calculator, it will give you back -3. Now let's take a look at a few properties of the log base a of x. So here we have some properties of the log base a of x, and you'll notice that they look exactly like properties for the natural logarithm. And that's because of the relationship between log base a and ln x that we just investigated. So first of all, log base a of 1 is 0, just like the natural log of 1 is 0. Log base a of x times y is log base a of x plus log base a of y, just like log base a of x to the y power is y times log base a of x. So in other words, you can drop this y out of the exponent just like you do for natural logarithms. And log base a of x divided by y is log base a of x minus log base a of y, just like the natural logarithm. Let's take a look at a proof of one or two of these. Let's prove number 2. Well, if we start out with, let's note that by our definition up here, that is actually equal to now by properties of the natural logarithm, we can write the numerator as and now we can split this fraction up as and now notice that this piece right here is by definition log base a of x using our definition up here. And this piece right here is log base a of y using the same definition. And we have our result right here. We've now just proven number 2. And all of the other ones are proven in exactly the same way by going back to our definition here for log base a of x and using all the properties for the natural logarithm of x. And so that concludes our discussion about the relationship between the natural exponential function and other exponential functions and the natural logarithm function and logarithms to other bases. So you basically need to remember these two important formulas. And so we'll be using these again. And that concludes this video.